In 1935, Albert Einstein and his colleagues published the EPR paradox, arguing that quantum mechanics was an incomplete theory because it required what Einstein called spooky action at a distance. This skepticism defined the field for decades, until John Stuart Bell derived a mathematical limit on classical correlations. Experimental violations of Bell's inequality proved that these non-local connections are physically real and measurable. This discovery dismantled the Heisenberg cut, the theoretical boundary that supposedly separated the microscopic quantum world from the macroscopic classical world. We now understand that the laws of quantum mechanics apply to all physical systems, regardless of their size. The 2025 Nobel Prize in Physics recognized this transition from theory to engineering. Researchers demonstrated that macroscopic superconducting circuits containing billions of electrons could undergo quantum tunneling. These systems act as a single, coherent quantum fluid, manifesting distinct energy levels on a scale visible to the human eye. This effect extends to mechanical systems as well. Engineers have successfully entangled two 10-micrometer aluminum drumheads, objects large enough to be seen under a standard microscope. By using microwave pulses at temperatures near absolute zero, the researchers forced these trillions of atoms to synchronize their motion, behaving as a single distributed quantum pendulum. Harnessing these macroscopic correlations is the core requirement for computational supremacy. However, moving from laboratory demonstrations to industrial utility requires a total overhaul of error correction architectures to reach the million-qubit milestone by 2030. Realizing fault-tolerant quantum computing is a challenge of industrial-scale engineering and precise environmental control. The underlying physics remains valid regardless of the system's size. The power of a quantum computer comes from how it scales. In a classical system, adding a bit increases the state space linearly, but a register of n entangled qubits exists in a coherent superposition of all possible basis states. This allows a quantum register to map a state space of 2 to the n complex probability amplitudes, creating an informational payload that classical hardware cannot track. The utility of this state space depends on the topology of the entanglement. Multipartite GH state states exhibit maximal global correlation, but they are exceptionally fragile. Measuring or losing a single particle causes the entire register to collapse into a classical mixed state. W states offer a more robust alternative. Their entanglement is distributed symmetrically across the network, akin to a triangulated grid. If one node suffers decoherence, the remaining particles stay entangled, making the W state a primary candidate for distributed quantum memory. This interconnected structure enables true parallel processing. Because the qubits are inextricably linked, a logic gate applied to one qubit simultaneously updates the correlations across the entire 2 to the n state space. The rate of entanglement growth is governed by the underlying complexity of a system's motion. In the quasi-classical regime, this growth is proportional to Kolmogorov-Sinai entropy, a measurement of classical chaos. While regular, non-chaotic systems generate entanglement logarithmically, chaotic systems generate it at a linear rate. This mathematical relationship identifies classical chaos as a specific quantifiable driver of quantum entangling power. This massive state space acts as the engine of quantum computing. Once a register exceeds 60 fully entangled qubits, the amount of classical RAM required to simulate its transformations surpasses the capacity of the world's most powerful supercomputers. This engine does not improve simple tasks like basic arithmetic. Entanglement is a specialized tool that specifically targets problems involving deep structural correlations and complex phase estimations. This graph compares the computational steps required by classical and quantum algorithms as problem complexity increases. For unstructured searches, Grover's algorithm uses a quantum oracle and a diffusion operator to shift probability toward the correct solution. As the solid pink line shows, this reduces the time required from a linear classical search to a quadratic square root. The scaling for prime factorization is even more dramatic. Shor's algorithm uses the quantum Fourier transform to map a periodic function across a massive entangled state. It converts the exponential time required by classical factorization into polynomial time, represented by this lower blue line. To reach these solutions, the system must hold the entire register in complex correlation through an orchestrated sequence of phase-shifting gates. These algorithms prove entanglement transforms computationally intractable tasks, such as factorizing RSA 2048 keys, from a requirement of thousands of years into a practical quantum operation. The primary obstacle to these operations is environmental noise. Any interaction with the outside world, from a stray microwave photon to a thermal vibration, acts as an unintended measurement of the qubit. This interaction, known as decoherence, leaks phase information out of the system. As this information escapes, the pristine entangled state is scrambled, irreversibly degrading into a statistical mixed state that behaves like a classical probabilistic bit. This process sets a rigid time limit on hardware operations, known as the coherence time, or T2. If the time required to run an algorithm's gates exceeds the hardware's T-sub-2 limit, the quantum advantage is lost and the output becomes computational garbage. To combat this, superconducting qubits are housed in multi-stage dilution refrigerators. These systems use liquid helium isotopes to cool the hardware to 15 millikelvin, significantly colder than the vacuum of deep space, in order to suppress thermal noise. Since perfect isolation is impossible, physical hardware alone cannot solve the problem. Mathematical error correction is the only viable path to scaling quantum systems. Quantum error correction encodes a single logical qubit across a large array of noisy physical qubits. By performing parity measurements on auxiliary syndrome qubits, the system can detect and correct bit or phase flips without ever measuring the logical state itself. Historically, this required an enormous hardware overhead. This gray bar shows the standard surface code, which requires up to 3,000 physical qubits to stabilize a single logical qubit for complex algorithms. To overcome this, the industry has shifted toward quantum low-density parity check, or QLDPC codes. As this tiny blue bar indicates, advanced bicycle codes can instantiate a logical qubit using only 60 physical qubits. The advantage of QLDPC is its constant rate and linear distance scaling. Unlike surface codes, these architectures maintain their efficiency as the system grows, requiring far fewer physical qubits to achieve the same level of error resistance. This efficiency comes with hardware complexity. QLDPC requires complex, non-local connectivity and ultra-fast classical decoders capable of closing the correction loop in under 480 nanoseconds. This architectural change makes the million-qubit milestone by 2030 physically attainable by reducing the required hardware and cryogenic infrastructure by orders of magnitude. Today, competing hardware modalities are racing to implement these codes. Superconducting circuits offer rapid gate speeds. Neutral atom arrays provide the 3D flexibility needed for QLDPC routing, and topological Majoranic qubits offer the promise of hardware-level error resistance. The most practical implementation of these technologies is the hybrid architecture. In these systems, classical high-performance computing nodes handle massive data processing, isolate a single intractable kernel, and dispatch that specific workload to the quantum processing unit for evaluation. Entanglement is already moving into metropolitan telecommunications. Projects like the Gotham Q network under Manhattan have demonstrated high-fidelity entanglement swapping over 17 kilometers of standard telecom fiber, establishing the first nodes of a secure quantum internet. The 2030 milestone of 1 million physical qubits will move these systems from experimental chemistry into industrial-scale utility, enabling the exact simulation of molecular catalysts and the design of next-generation physical materials. The commercialization of entanglement provides a processing infrastructure that extends human capability beyond the limits of classical simulation, enabling us to model nature and secure information with mathematical certainty.